From the beautiful North Studios of Way Happy, this is Mr. Meyer, and we're talking 3 increasing and decreasing functions in the first derivative test. So let's get started. We've talked about when a function decreases or increases, and probably the easiest way to think about it is if there's a little man walking on it, right? If he's walking on that mountain or whatever, on that graph, if he's walking downhill, then you're like, oh, look, it's decreasing. And then if he's walking constantly, remember we always go left to right. So if he's walking straight along, that's constant. And if he's walking uphill, I like to call that increasing. So that's what we do with the little guy, right? That's a pretty informal way of talking about, what a graph does or when it's increasing or when it's decreasing and stuff like that. So how can we tell? Well, notice something fancy about these increasing slopes, right? There's a slope, there's a slope, there's a slope, right? What are all these slopes doing? Well, they're all increasing, but they all have something in common. They all have a positive slope. What about the decreasing slope side? Look at these tangent lines right here. They all have what we would call a negative slope. And I guess if you want, the ones in the middle, the constants, they all have zero slope. So it would be really easy to tell when a graph is increasing or decreasing if you looked at the slopes. Wait a minute, we know how to look at slopes, right? We know how to look at slopes because we look at the derivatives, and that's what we have down here in this theorem the book calls increasing or decreasing functions. It says, hey, look, if the derivative is positive, greater than zero, then your graph is increasing. If the derivative is less than zero, then it's decreasing. And if it's equal to zero, then it's constant. And what's really important about those constant points, or these equal zero points, is that they're critical points. They're kind of where the graph has gone from being a negative slope to a positive slope or something like that. So these critical points that they create are kind of awesome. And that's when the derivative equals zero. All right, let's see. Example 1. Find the open intervals. We like to use open intervals a lot of times for these, just not using brackets, using parentheses. For that graph when it is increasing or decreasing. Okay, how would I tell? First off, we got to worry about if it's continuous, because discontinuities, like an asymptote, on a graph, your graph could be going from increasing slopes definitely to decreasing, and it's not happening at a critical point because there's an asymptote there, which is a discontinuity. It could happen at a jump. So there's things that could make us we have to be a little careful. We have to talk about constant. If we're going to talk about increasing and decreasing over a continuous function, would be much more helpful, but be a little careful. Sometimes there could be a discontinuity in there that messes you up. I'm looking at number 1 going, that thing's continuous. I know because it's a cubic, right? So I know that's a continuous function. And that's, if you look to the right here in this box, it kind of talks about little things, but first thing in there in the highlighted area that I'll highlight, it says, let it be continuous. So, all right, this is definitely a continuous function. Find the critical points. All right, where are those critical points? Where are those critical numbers? They are when the derivative equals 0. So real quick, I'm going to take f prime of that. And what is it? 3x squared minus the 2 out front minus 3x. All right, now what I want to do, if I want to find critical points, then I am going to set that equal to 0. So I set that equals 0. Let's see, what can I do? I could divide everybody by 3 if you want. X squared minus x equals 0. And then I factor out an x minus 1. Ooh, look at that. We found critical points when x is 0 and when x is 1. Those are what we call critical points. Now, what does that mean? This is a continuous function. This continuous function goes on forever, but at 0, but at the beautiful number 0, this graph has a critical point, and it has a critical point at the number 1. So at these points, we have a critical point. Something is happening to the slopes, right? Well, it's really easy to check then things on the other sides of the slopes. And so what I'll do is I will say, all right, pick something smaller than 0, like -2. Pick something between 0 and 1, like a half, and pick something bigger than 1, like 10. And plug them into this equation, this derivative, and decide if it's positive or negative. So when I plug in -2, I'm going to get a negative times a negative, right? I'm going to get -2 times -3. I don't really care about the numbers. I just care about the signs. So I get a negative times a negative. All of these things are positive. When I plug in a half, I'm going to get a positive times a negative. So all these are negative. And when I plug in 10, I'm going to get a positive times a positive. All these are positive. So if you notice, we are talking about the slopes of the graph. The slopes are positive up to 0. We have positive slopes when we get to 0. But then we have negative slopes after 0 all the way to 1, and then we have positive slopes after 1. So what does that tell me? That tells me we are increasing on this graph from negative infinity to negative 2. We have a positive slope happening. I'm going to use open interval. And it's going to happen again when you get to 1 all the way to infinity. You will always have an increasing thing. And I haven't even looked at the graph. I kind of know what the graph looks like. It's x cubed, right? So I kind of know the graph goes like that. And it makes sense. It's positive up to a point. Then it went negative slopes for a little while, and then it goes positive again. So it's decreasing when those slopes were negative or when the derivative was negative, and that was between 0 and 1. So that's how I could tell you when a graph is increasing or decreasing just by looking at the derivative. So now I don't even need to see the graph. I can just say, hey, look, let me take the derivative real quick. Let me see when it's positive. Let me see when it's negative. And I can tell you when that graph is increasing or decreasing. How nice is that? All right, let me ask you a question, and I'll be right back. All right, nice work on that one. Now let's talk about that. You can see the little note there in your notes is fancy vocabulary. We can say something is strictly increasing or strictly decreasing, or we could call it monotonic. So monotonic is a fancy word for saying it's increasing or decreasing the entire time. All right, what about this? The first derivative test, that's a big one, right? It's pretty self-explanatory though. I don't think it's going to spook us too much. What does it say? It says that if you do all this math, right? You find the derivative and you find the critical points, and then you look at the left side is increasing and your right side is decreasing, and then the next part of it is increasing again. It's telling you about maximums and minimums. I mean, think about it. Look at this first part here. We have slopes that are definitely negative until all of a sudden they hit 0, and then they change to positive slopes, right? So you've gone from having a negative slope to a positive slope. What would that tell you? Well, that would tell you at that point where it was 0, that point has to be the lowest point. It has to be a relative minimum, right? Because you went from negative slopes to 0 to positive slopes. So that's an easy way to find a minimum. Or the other way around. What if the slopes were positive? So here they are, they're all positive slopes, and then all of a sudden they switch to negative slopes. What? If you noticed that on like a table of values or a number line, you would know that you just found a maximum because the slopes have changed. Now, what if you had a critical point and then you evaluated the left side and you had positive slopes like you do here, and then all of a sudden you evaluate the right side expecting negative slopes and you have positive slopes again? Then you found neither a maximum or a minimum. I like to call it a point of inflection. So that is what we're going to do here on example 2. Find the extrema. So I got this crazy graph, a half minus sine x. Oh, I don't know what that looks like. Well, I kind of do. It's a sine graph that's inverted and it's shifted up a half. But I want to know what the extrema are for that graph. So let's find out where the critical points are. First off, I know sine is continuous, so I know it's a continuous graph. I'm feeling super good about that. So I should probably say, hey, this graph is continuous over the interval, open interval, 0 to 2 pi. Let's go ahead now and talk about where are those critical points. So what I need to do is take a half, take the graph, and actually find the derivative. So derivative of half is nothing. The derivative of sine is cosine. So it looks like negative cosine of x. So if you want to find critical points, when does cosine of x equal 0? You can get rid of that negative because it doesn't matter now. Divide both sides by negative, it's gone. So when is cosine 0? So I got to think about that for a minute. When is cosine 0? Well, cosine's my top finger, so it's going to happen at pi over 2. And it's going to happen at 3 pi over 2. Those are the two times that cosine would be 0. So here's my number line, right? This time I only need my number line to go from 0 to 2 pi, so that's kind of cool. So that means here's 1 pi, and here would be pi over 2, and here would be 3 pi over 2, or 1.5 pi's. So right there is where a critical point is. Now be careful when you do your testing. Remember, I always say like, oh, test everything to the left, but I got to stay between 0 and 2 pi. So I got to make sure I'm in between there. So something smaller than pi over 2, but is before 0. And so I will take pi over 4 into account. Something between pi over 2 and 3 pi over 2, I will test out pi. And I want to put that on the bottom. And something between 3 pi over 2 and 2 pi over 3. What do you want? Let's do a fourth less than 2 pi. So that would be, what is 2 pi? That's 8 pi over 4. So 7 pi over 4. All right, let's test those. If you were to test pi over 4 and tell me the cosine, you would get root 2 over 2. And according to all students take calculus, since pi over 4 is in quadrant 1, all the trigs are positive, so you're good. All right, let's take pi. Pi has a reference angle of 0, right? So 0, cosine is 1, but since it's over here on this side where sine and tangent are positive, cosine is always negative, so it's negative over there. And then last but not least, 7 pi over 4, that's down here in this quadrant where our good friend cosine is positive. So therefore, I know the answer is positive. And there you have it. You have now found the critical points and you have found the increasing and decreasing. So if you wanted to, you could say, hey, look, the graph is increasing from 0 to pi over 2, and then again from 3 pi over 2 to 2 pi. You could say it's decreasing from pi over 2 to 3 pi over 2. But what we wanted to talk about is there a maximum or a minimum? And just look up here. We went from positive slopes, right? The slopes were positive, to all of a sudden going to negative slopes. So that means pi over 2 is a maximum because we went from positive slopes to negative slopes. And over here, I had negative. We were going negative, so we had negative slopes going down, 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 down. Then all of a sudden, we changed to positive slopes. Hey, look, that must be a minimum. So I know 3 pi over 2 is a minimum. And so that is how I could tell you if a graph has a minimum or a maximum over the interval. That's it. Stay happy. I'll see you tomorrow.